directors, and it's a pleasure for me to introduce today Sara Mouradian, who is giving the fall doctoral dissertation seminar of MTL, which is an award that we give in MTL every term to select a very impressive thesis defense that was done in the last few months to be done again in front of this community. So Sara graduated from the Cambridge Group earlier in the year. Her research investigated scalable solutions for diamond-based quantum information processing with integrated photonic circuits, which is the topic that she will describe us today. She holds bachelor's and master's degrees also from MIT and ECS. Between her master's and her PhD, Sara spent 6 months at the Max Planck Institute for the Science of Light in Germany. And Sara is now a postdoc at UC Berkeley, working on novel architecture for trapped ion experiments. I want to give you this award now, Sara. We can get this picture here. So congratulations on being selected for the doctoral dissertation seminar. Full resource.
Great. Well, thank you everybody for coming, and thank you to MTL for giving this opportunity to come back. It would have been perhaps nicer in the summer, but it's good to see what I'm missing. So today I'm going to be talking about what I did during my PhD work on improving the scalability for solid-state systems for quantum information processing. So before I begin, I'd like to thank everybody who made this possible. So of course, my PI, Dirk England, who gave us the resources needed to do this. Tim Schroeder, who is a postdoc, especially at the beginning of this work, who really taught me a lot about doing experiments in the lab. Igal Bain, who taught me everything basically I know about fabrication. And Noel, we worked together in the fab a lot, so all the fab that you'll see was done with him. And then Michael and Eric, who helped write code and helped me do experiments, and also everybody in the lab. So everyone here, I'm sure, has heard a lot about quantum information processing. There are 3 special things about quantum systems that allow them to have advantages over systems that can be described purely classically. And so the first is this idea of superposition, whereas a bit can be only a 0 or 1. A qubit can be a superposition of 0 and 1, where these coefficients a and b can either be real or imaginary. The second is this no cloning theorem, whereas we can amplify classical signals without knowing what they are a priori. We cannot do the same with quantum signals. So if I give you a quantum bit, there's no way that you can take it and make 10 quantum bits that have exactly the same state. And the third is this idea of entanglement, which is basically a stronger than classical correlation. So with these, you can improve many aspects of information processing. So the first is sensing. So for instance, during my master's with Professor Jeff Shapiro here at MIT, I worked with Zhixin Zhang to demonstrate the first implementation of quantum illumination in the optical realm, where we showed that if you start with an entangled pair and you send half of it to see if there's a target somewhere in the distance, you can get a higher signal-to-noise ratio than you could with just classical light. And that's even, actually especially in situations that are very noisy and very lossy. So those are usually the kind of situations that you think quantum systems fail in. But we showed that you can actually get an improvement. The second is in secure communication. So if 2 people, Alice and Eve, of course, Alice and Bob, share a quantum channel and a public classical channel, they are able to share and produce a provably secure key, even if Eve is eavesdropping on the channel. And then finally, we have quantum computation. And there are 2 kind of paradigms of quantum computation. The first is simulation, where you build up an engineered quantum system in order to model and understand more about a system that nature gives us. And the second is universal quantum computation, which is a little bit more like digital classical computation, where you can run algorithms. For this to provide an improvement over classical systems, we need precise individual control over every quantum bit, and we need the engineered coupling between quantum bits to be much stronger than the coupling to the environment, the dissipative coupling to the environment. And we need to do that for, in the end, millions of qubits. So this is a huge engineering challenge. There are many ways that people are working on to make this happen. We haven't really settled on our quantum transistor yet. So there's superconducting qubits, trapped ions and neutral atoms, that's what I'm working on now, quantum dots, photons, and today I'll be talking about defects in diamond. And of course there's a lot of university groups working on this and also a lot of industry money. Whenever you look at a press release from a company or at a new result from a lab, there are three things you should ask yourself. The first is how many high fidelity gates can be performed in the system within the coherence time of the qubits. The second is how many qubits do they have and how good are their qubits? It's one thing to have 1,000 qubits, but can they actually all be used well? And the third is the connectivity. How are they connected together? Do you only have next neighbor interactions, or can you get connections over the full graph of the system? So today I will be talking about my work in this field. So I'll start off with an introduction on quantum information processing with the NV Center, the Nitrogen Vacancy Center in Diamond. I'll then show how I increased or worked to increase the number of gates that can be done during the coherence time of the NV Center, and that's by integrating these NV centers into nanophotonic structures in Diamond. And then I will talk about how to increase the number while maintaining high quality of the qubits in a platform, and this is through hybrid photonic integrated circuits. And I'll finally, very briefly, talk about what I'm doing now at the end. So the system that I will talk about during this talk was the negatively charged Nitrogen Vacancy Center in Diamond. So before I talk about what the NV Center is, first I'm going to talk about why Diamond is so good. And the reason is basically that we can produce more or less perfect CVD, chemical vapor deposition grown diamond. So we can create this diamond such that it is almost completely pure, so fewer than 1 part per billion defects in the diamond to begin with. And it can be isotopically pure as well, so there is no carbon spins to complicate the situation, or very few at least. And then the second, and then how we create the NV Center is we replace one of the carbon atoms with a nitrogen atom, and next to it is a vacancy. And this creates a trapped 2-electron system or a spin-1 system that we can use for quantum information processing. So on the right here, we see a simplified level diagram of this NV Center.
There's a pointer.
Oh, yeah, I think, yes. The simplified level diagram. So we save the information in these ground state levels that are split even at zero field by around 3 gigahertz, and we can split out the plus and minus 1 states with the application of a B field. And we also have these optical transitions. And so this is in red around 637 nanometers, and we'll use that to create entanglement between remote NV centers. And then finally, we can also excite above band with green, or 532 nanometers. So there are a few things that make the NV Center so good for quantum information processing. The first is that we can initialize the qubit with very high fidelity. If you notice, there's a state over here. So the ms equals 0 spin state is more or less cycling. So if we excite it to the 0 state, it'll fall back down into the 0 state. Whereas the ms equal plus minus 1 states are coupled to this long-lived singlet state, which then decays into the ms equals 0 state. So if we just pump with green enough, anything that's we'll pump all of the population, all 0 and 1, into the excited state, and then the 0 will fall back to the 0, and some of the 1 will fall back into the 0 as well, and so if we wait long enough, we can get perfect pumping into the initialization into the ms equals 0 state. The second is that this electron spin has coherence times that are longer than a millisecond. We can do 100 microseconds, couple hundred microseconds pretty easily in the lab without trying very hard. And we can also couple this electron spin to nearby nuclear spin, which can have coherence times much longer, up to a second. Maybe even longer if we try even harder. And then finally, we can entangle this spin state with the state of the photon. And it is this property that we'll use to create entanglement between different NV centers. So let me explain briefly how this works. So what we first do is we do a pulse here to create a superposition in the electron spin state between 0 and 1, and we do that for 2 NV centers, so they both have superpositions. We then excite only the NS equal, well, only one of the transitions, and that moves the superposition of the spin state into a superposition of the occupation of a photon mode for both channels coming from each NV center. Then we put these two optical modes on a beam splitter. This erases any information that we had about the origin of the photon. So then if we get a click that says we only have one photon, we don't know which one it has come from, so we have created a fully entangled state between NVA and NVB. And there are some tricks that we can play to make this more immune to loss and noise, but that's the basic idea. So those are some good things about NVs, but there's of course also bad things about NVs. As you noticed, we really need to imprint the state of the spin with very high fidelity onto the state of this photon. However, if you look at the optical spectrum that comes out of this NV, you'll notice a few things. One, we see kind of what we'd expect, a very narrow transition. This is what we call the zero phonon line. So this is the exact transition from the ground to the excited state, or the emission from the excited to the ground state. But we also see this broad sideband, which we call the phonon sideband. And that's because although the system is nice, it's still trapped into a lattice. So we can still couple the spin to the lattice. So you get these phonon transitions. So any photon that comes out in this phonon sideband comes from a decay event plus a phonon decay. And when that phonon decays, it loses all its information to the lattice, and so that photon cannot be used for quantum information processing. So we can only use these photons, and that's unfortunately only 3% of the emission of an NV center in bulk. The second problem is that the NV is a dipole, and dipole emission is notoriously difficult to collect into a single optical mode that can be used for transport, such as a waveguide mode or a fiber mode. And the third thing is that we have something called spectral diffusion. Spectral diffusion is when there's moving electronic fields nearby, which shifts the levels of the NV center, changing the frequency of this transition ever so slightly. So because of that, currently the entanglement rate is limited to much less than the decoherence rate. We can, maybe if we try, do 1 every second or 10 seconds, or that's like the fastest that anybody in the world can do it, but that's not fast enough for creating multiple entanglement events within the coherence of the qubit. So now, one thing that we can do to improve that is couple the NV center to a cavity. So a cavity is an optical cavity. So a cavity will give you two things. The first is increased emission at the resonance frequency of the cavity. So this is the Purcell effect. It's proportional to the quality factor of the cavity, or how long the light stays in the cavity, over the mode volume of the cavity. The second thing is that we can engineer the loss of this cavity into a useful mode. So we can say we can create a very, very high Q cavity, but then introduce a loss mechanism into, for instance, a waveguide mode or a fiber mode. And then these two things together will give us an increased rate of entanglement. But now we have to make this, and as you noticed, it's inversely proportional to the volume of the cavity. And so we want a very small cavity. And so of course, then we want a nanophotonic cavity, and then we need to create a nanophotonic cavity. So how we do it, instead of using a big Fabry-Perot mirrors, we create a photonic band gap. And so this is created with a periodic modulation of the index of refraction. And we create a defect. And so this stops light propagation at a specific frequency. And then we create a defect in the center, which allows light to stay only at the center and not propagate into this mirror created by this photonic band gap. So in simulation, you can get very high Qs, bigger than 1 million, and very low mode volumes around the size of the wavelengths within the material. So this cavity is a very similar cavity to the one I saw before. You can't really see the defect as well though, but the spacing between these holes is slightly smaller than in the band gap out here. We can also remove the holes on one side in order to get most of the emission into one direction out of the waveguide. So these look good in simulation, but now we have to fabricate them. Unfortunately, diamond is notoriously difficult to fabricate for a few reasons. The first is that it cannot be grown epitaxially, or high quality diamond cannot be grown epitaxially. So unlike silicon, so if you think about silicon processing, often you'll have a wafer with a layer of silicon dioxide and then a layer of silicon on top. So you can have that, that optical confinement immediately. And you can also under etch that silicon oxide if you need, so you have that beautiful layer system. We don't have that for diamond, unfortunately. The second is it's fairly chemically inert, so it's a bit of a pain to etch without just ruining all the properties. So there's a few ways people have done it. People have used membranes, and they make those membranes by taking a big chunk of diamond and then just thinning it down, first mechanically and then chemically, and it takes a long time, and in the end, you're left with a diamond that is thin but has a lot of variation over the wafer. And when I say wafer, these are really only, in the end, you get these little pieces that are 100 microns big, so they're really a pain to work with. But our group did very impressive work also with those membranes. The second is this triangular etch. So what you do is you start with a bulk diamond, and you etch at a slant from both sides, and so you create a structure that is, fully suspended but has a triangular shape, so you get these kind of Toblerone-looking structures. So Harvard has pioneered this, and we have also shown decent cavities with this. Unfortunately, you get a kind of strange mode structure that is difficult to couple into other photonic structures. And also you can get more surface roughness because it's a pretty rough etch. And so the way that we worked to make optically isolated nanostructures from bulk diamond is with what we call a quasi-isotropic etch. So I'll explain that to you now. So the main point of this quasi-isotropic etch is that we use a plasma etch, but with no bias. And so that gives us an almost purely chemical etch, and in all directions, and that means that the etch rates are dictated by the etch rates of each plane. So we see that the 110 plane etches fastest. So if we are in a 100 diamond, so that means the top face is 100, we align all our structures along the 110 plane. So that means that this plasma etch etches in much faster than it etches up. And so that's why in the end we'll be able to make these rectangular structures. So to do this, we use a silicon nitride hard mask on top of our big bulk diamond. When I say big, I mean a couple millimeters, so it's still pretty small. But at least you can use tweezers and stuff to pick it up. But we start with a silicon nitride hard mask that we pattern with ZEP and the EBL. We then do an anisotropic oxygen etch. So this is an etch with a bias, and we can get nice straight side walls. It doesn't degrade our silicon nitride mask too much. So you can see here in SEM, this is our silicon nitride mask and the diamond underneath. We then cover everything with 20 nanometers of aluminum oxide with atomic layer deposition. This allows us to cover everything and also cover these little holes conformally. So these holes are about, now I forget, it's been a while, 200 nanometers, let's say, or smaller. So we need something that will conformally coat also into the holes. We then do a breakthrough etch to etch off the top surface and this surface here while maintaining coverage of the side surfaces. We then do a second anisotropic etch just to give us a little bit more diamond exposed. And then this is the part that allows us to get the suspended beams. We do this isotropic option F, or quasi-isotropic, because it does have a directionality depending on the facet of the diamond. And so, as I said before, this direction etches much faster than this direction. So we get these funny triangle-shaped structures, but if we etch enough, this will go up the triangle will etch away faster than this bottom surface here. So in the end, we'll get a rectangular cross-section. And so this is a scanning electromicrograph at kind of this stage, where you can see the sheath of the remaining ALD. This here is diamond with ALD on top, and then the remains of our silicon nitride mask. And then, so it continues, it's rectangular, and then we take off all the masks with HF, and we see a nice rectangular cross-section, and we can create very large, totally suspended structures. And luckily diamond is very hard, so we can actually create even longer than this. This is, I think, about 10, maybe 15 microns, but we can create, and Noel's done a bunch of this, huge structures that are fully suspended. And this is also only suspended on one side. And these are only 50 nanometers, just to give an idea. So you can see these nice SEMs. They look really good. The question is, do they work? So we first did this we first made these cavities in lower quality diamond, which have a lot of native NVs, so hundreds of NVs within excitation spot. So, and that makes it easier to test these. So we excite with green, and so that's this above band excitation, and we collect in red. So we collect the emission of these NV centers. And then we can look at a spectrum. And what we see here is we see this NV-ZPL, what we saw before. This is just from the NVs, and then we see these other peaks that aren't there in bulk diamond, and those are the 4 modes of our cavity. So the first order TE mode, which is the one that we optimize for, a TM mode, and then 2 higher TE and TM modes with modes isolated in the mirror region. So what we care about is the quality factor of this. And so we can measure with a spectrometer up to around 14,000, and that's what we measure, a Q of 14,000. So the actual Q might be a bit higher, but we already know that it's 14,000, which is and still is a record for diamond nanophotonics invisible wavelengths. The other thing, of course, about fabrication is you don't only want to make one hero device. You'd like to be able to make many devices on the same chip and have them all work out. And so we measured all the devices on the chip. We made a couple with many different parameters. So we changed the width, and we changed the hole diameter. And we see that we have very nice scaling. And, as the width increases, our resonance wavelength increases as well. And the opposite for the hole diameter, which is what we expect. And we also see a very small spread in the resonance frequencies, which shows that we have consistent fabrication. And this spread should be small enough to be able to tune with gas tuning any of these cavities to the resonance we want, or any of these cavities that are targeted to be the right wavelength we want. So we've done this fabrication in diamond with many NV centers. So the structures that I just showed you cannot be used for quantum information processing because it's impossible to isolate just one NV center. So we do this again in diamond with just a few NV centers at the depth that we want, that we make by implantation. And we want to make sure, or we would like to have NV centers with bulk-like properties in these nanostructures. So what do we mean by that? So now we're back to the issue of spectral diffusion. And the worry is that all the surfaces that are now nearer to the NV center, because we've done all this fabrication, will have more defects, which will cause more electric field fluctuations, which will then cause more spectral diffusion. And so what we'd like to see is that the line width of a single NV center is what we expect by looking at the lifetime. So we call this the lifetime limited line width, which just means that there's this the relation, and we know that the lifetime is about 13 nanoseconds, so we think that you'd hope that the NV LIDOS would be about 13 megahertz. And so that's what it should look like. Unfortunately, if we measure an NV, this is what it does look like. So this is if we take many measurements at each frequency, and build up statistics at each frequency, we see a very broad line, or if we just do quick scans over the resonance, we see that it hops around a lot in time. And so this would not be good for quantum information processing, because you can see that every successive entanglement attempt, there'd be a slightly different frequency, and so we could tell, when we measure one photon, we can tell which NV center it came from, because the two NV centers will have slightly different frequencies, and so we don't get high fidelity entanglement. So we want to investigate this a little bit and see how good we can get these nanostructures, and see if there's any hope of getting a high quality NV center in a cavity with high Q and low mode volume. So first, let's just look at NVs in single mode waveguides. So that's a structure kind of like this. So you'll see no holes, but it's still a single mode waveguide with a cross section of about 250 by 250 nanometers. So the first thing that we see is if we look at the wavelengths of all the NV centers that we find before annealing the sample after fabrication, we can see a pretty large spread. After we anneal it, we see that the spread decreases, and most are at where we expect, around 637 nanometers. And so that shows us that we had some strain in our sample that we were able to remove through annealing. So that's a good first step, at least. Second, we look at the line widths, and we look at the line widths in bulk, so that's these blue, as well as in waveguides. And we can see, while we do get some low line width NV centers in waveguides, definitely the distribution has shifted towards larger line widths. So although we can get down to 265 megahertz, which is still kind of 20 times higher than they should be, we see that there is this increase in line width. Unfortunately, this gets even worse with cavities, because in cavities, the NV center is even closer to surfaces. So for a optimally placed NV center in what we call an L0 cavity, it would be within 30 nanometers of the hole surfaces right next to it. Oops. Maybe we should move more. And so when we look at NVs in what we call an L0 cavity, we see even broader line widths, so up to 30 gigahertz, tens of gigahertz. And so that is not good for quantum information processing. But when we look at L3 cavities, we see that we can recover the line widths from the waveguides. And that makes sense because here, NV in an L3 cavity kind of looks like it's in a waveguide. It's around 100 nanometers from all surfaces. Unfortunately, this L3 cavity has low intrinsic Q, so even in simulations, we could only get Qs around 6,000. Not that I tried particularly hard, but it's definitely lower Q than the L0 cavity. And in fabrication, we get Qs of around 600. So while we can get more decent line widths, the quality of the cavity itself is worse. So that inspired us to create what we call alligator cavities. And so instead of creating this periodic modulation of the refractive index with holes, we create it with this sinusoidal modulation on the outside. And then we so that creates the band gap out here. And then we create a defect in the center by changing the depth of the modulation linearly over 5 periods. And so that concentrates this mode at the center here. So this is an SEM of such a cavity. And so these cavities have a few advantages. The first is it looks basically exactly like a single mode waveguide. You're more than 100 nanometers from the top, bottom, and side surfaces, and microns from the end surfaces. Also, it's a little bit easier to fabricate, or it should be, because you don't have to create holes. And if you've done a lot of fabrication, creating these high aspect ratio structures is always the least fun part, because you need to etch in these small little areas without ruining your map. And also in simulation, we can get quite high Qs, so around 10 to the 5th And so we fabricated these and measured them, and we can see that we get Qs around 10,000. This was the first fabrication run, so it seems like it has good possibilities for the future. Unfortunately, I didn't get it around to doing this in diamond with single NVs, but we hope that this will give us both the line widths of waveguides plus the high Qs of a high Q cavity. Yeah. So I have showed you how we're working towards increasing the number of gates or the rate of entanglement versus the rate of the decoherence by putting these NV centers into nanostructures. And now I'll talk a bit about how we can start hooking up these qubits together in a more scalable way. So when we think about scaling quantum computation, it looks a bit daunting. This is a lab with one quantum bit. You have this big laser here and a big laser there, there's a cryostat somewhere. You need a second whole optical table for a second quantum bit. That's not great. You can get up to tens, and Google said they had 72 qubits. I think IonQ just came out with a press release of maybe 79 qubits. At some point, somebody might come out with 80 qubits, but it's still pretty small. It's because to do really fault-tolerant universal quantum computation, in the end, you'll need millions of qubits. So how do we get there? Luckily, we have classical computing to take advantage of. So I'm sure in the 1940s, classical computing looked just as silly and daunting. There was, 1943, there was this computer. There were 1,500 tubes, and there was one room, and it couldn't do very much. Then the transistor was invented somewhere in here. They created the first integrated circuit. In the 1970s, they introduced VLSI, which really allowed us to start thinking about large-scale systems. And now, IBM has this chip with 30 billion transistors. And in this room alone, there's probably almost 500 billion transistors between our phones and our computers and everything. So it hasn't been that long in some sense. And we've gone from 1,500 tubes in one room to 500 billion. So we can take some solace and some inspiration from this story and try to bring that to quantum computing. So right now, most experiments are done in bulk systems, free space and fiber systems, and that's because these systems are easily implemented and well understood. We can, go on the Thorlabs website and order everything we want and have an optical setup within a week. Unfortunately, they're bulky, lossy, and unstable. So we can move to integrated circuits, and of course there's many engineering challenges that come with that, but in the end you get a system that's compact, low loss, phase stable, and you can also use all that classical computing CMOS infrastructure to get on-chip logic and on-chip control of your system. Because even if it's a quantum system, you still need a lot of classical control. So now when we look at the timeline, it looks a little bit more exciting. We can call something like QVLSI, just to make ourselves feel good. And now it looks exciting to move to millions of qubits instead of scary. So now we need this integrated quantum architecture. So we'll have integrated quantum nodes with both microwave and optical control for our NP centers, optical routing and detection, and then classical logic that controls all this and does some sort of feedback. So there's two ways that you can think about building this. The first and most obvious is with a monolithic photonic architecture, where everything is fabricated together. Unfortunately, as I've just told you, diamond fabrication is hard. And also, not every node that you fabricate is perfect. Not every NV is perfect, not every cavity is perfect. And if you're fabricating everything together, the success of a network with n nodes scales exponentially. So if you are only creating a good node 1% of the time, which for NV centers is high, even to get 5 successfully connected nodes, you need 100 to the 5th devices. You need to try like 100 to the 5 times before you get one. The second thing you could do is a hybrid photonic architecture, where you fabricate the components separately and pre-characterize them, pick the 5 best ones, and then integrate them into a pre-fabricated photonic integrated circuit. And so this scales linearly with the number of nodes, and so you just need to make 500 nodes, pick the 5 best ones, and put them into your circuit. And making 500 nodes is not that bad. We can fit 5,000, even more, on just one chip. So that's what we ended up doing. So the results that you'll see here were done with silicon nitride in a platform that was fabricated by Michael Lipson's group, then at Cornell. There are also other options. So what we need out of a photonic backbone platform is we need it to be easy to fabricate, so that silicon nitride was. We also need it to be low loss in the visible, so the three that we consider were silicon nitride, lithium niobate, and aluminum nitride, although there could be others. We would like it to have low background fluorescence, since we're going to be shooting a fair amount of optical power through these waveguides. Unfortunately, as you'll see, silicon nitride is not low fluorescence. It has a lot of defects, not pure crystalline, whereas lithium niobate and aluminum nitride both are low fluorescence. And you'd also like it to be active, so you can do a lot of this routing on chip. So you can say, okay, now I want to connect nodes 1 and 3, and after I create entanglement between those nodes, I'd like to connect nodes 1 and 4, for instance. And both lithium niobate and aluminum nitride are active. So now in the lab, they're starting to work with those two materials. But the results I'll show here are with silicon nitride. So we have the platform in silicon nitride, and we have these arrays of waveguides, diamond waveguides, some with NV centers. And so this is a scanning electron micrograph, and this is a confocal microscopy image of the same array, or a similar array, where we're scanning a green laser across and collecting fluorescence. So all these bright spots are NV centers. And you can see already that the yield of the nodes is very low, so there's only a few here that we could even think about using for quantum information. So let's say we want this one because it has this nice NV center near the center. So what we do is we pick it out with a tungsten probe. We then bring it over to our nice platform with our silicon nitride waveguide, and we place it down with our tungsten tip. So here it is on the tip. Here's our single mode silicon nitride waveguide, our single mode diamond waveguide, and our tip placing it down. And in the end, we can get high precision placement. So we have low yield node creation, but we have a high yield integration process. So in the end, we're able to get a high yield final product with multiple diamond nodes on one photonic integrated circuit. So unlike a monolithic photonic integrated circuit, you also have to then convert the mode of the diamond photonic structure into the mode of the silicon nitride backbone. And so we do that with these tapers. And so these tapers adiabatically convert the mode in the diamond waveguide that is confined here into the silicon nitride waveguide here. So we can get a full 82% of emission coupled from the NV into the silicon nitride waveguide. So that's 86% of the NV into the diamond waveguide, and then 95% from the diamond to the silicon nitride. And this was all done without cavities, so just pure waveguides. But of course, this emission could even be enhanced by a cavity, and the rate could increase. So to validate our system, we did a few measurements. So this is first a saturation measurement, because it's so we increase the pump power. So this is the power of the 532 nanometer light. And we collect light both through a kind of standard collection system, through an objective from the top, and also through the waveguide. And so here is the raw data, and here is after we account for losses in the system. So what we're actually measuring here, what we're plotting here is collection into the objective and collection into the waveguide. So it's taking out the effect of the coupling from the waveguide to a fiber and from the objective into the rest of our optical system. So it's collection into the first optic. And you can see that there are 3.5 times more photons collected into the waveguide than into the objective. And so this is just a proof of principle concept, but it shows that this really allows for high rate collection of photons into waveguides. We also did what we call an autocorrelation measurement. And so that's to show that the photons that we collect really come from the NV center. And so because the MV is a two-level system, it can't emit two photons at once. So if we time tag all our photon arrivals and then correlate those signals, we expect to see a dip at zero because there can never be two photons that arrive at the same time. So a correlation between collect half here and half there, there'll never be any that arrive at the same time. And so when we do a confocal autocorrelation, so that's collecting the normal way from the top, we see, as we expect, a big dip at zero. When we do a cross correlation between the photons we collect from the top and the photons we collect through the waveguide, we still see a dip, but the dip is reduced. And that is because, as I mentioned earlier, silicon nitride has a lot of background. So when we're exciting this waveguide with the green light to excite the NV center, we're unfortunately also exciting defects in the silicon nitride, which also produce broadband fluorescence, which we then collect, which reduces the quality of the photons that we collect. So what I showed so far is we have the photonic integrated circuit and we have the diamond, but they don't really interact in any way. But we can also think of building up more complicated structures. So for instance, a structure like this where we use aluminum nitride has a very strong piezoelectric property, so we could use that to create really hybrid photonic structures. And so in this is another photonic crystal cavity. And now we create a band gap. So the band gap is created here, so you still see this periodic modulation. But the periodic modulation is happening all in aluminum nitride. And so we don't need intense fabrication in this diamond in the center here. But luckily, diamond has a high index of refraction, which pulls the mode into the diamond. So when we increase the diamond width slightly at the center, we get this localized mode in the diamond at the center of this cavity. And so with this, we can get very high Q cavities, larger than 1 million. This structure limits the patterning needed in the diamond. And also we can use the MEMS in aluminum nitride to tune the resonance. So this is all on simulation, but as we move these two bars in and out, we're able to tune the resonance over 40 line widths. And so, right, in this simulated structure, in pure nanometers, that isn't much. But if we want to sacrifice tuning or sacrifice Q for tuning, we can create a lower Q device that is tunable over a larger overall nanometer range. And we can also, then we have direct connection into the underlying aluminum nitride photonic integrated circuit. We can remove the holes on just one of the 4 arms of the aluminum nitride photonic crystal cavity, and we can load the cavity directly into the aluminum nitride photonic integrated circuit. So we can get more than 75% of the cavity light coupled directly into the aluminum nitride waveguide. So that sums up the photonic integrated circuit part. So we've shown that we can get a high number of high quality qubits. And in the future, it would be nice to add more active components, like actual RF generation for controlling these qubits, as well as on-chip detection and logic. And so, just to summarize what I did during my thesis, we showed how you can improve the number of high-fidelity gates by coupling to cavities, and we still need to fix spectral diffusion to really make that happen. And then we can also increase the number and quality of qubits in a system by using hybrid photonic integrated circuits. But it would be nice to add more functionality. And now I'd like to talk really briefly about what I'm doing now. So now I'm at the ion trapping group with Professor Hartmut Hefner at UC Berkeley, working on 2 things. The first is a ring trap. And in this trap, I have a cool animation. We can prepare and control angular momentum states of these ions. So usually you think of ions in a long chain, and you can control their harmonic oscillator modes occupations, but now we can control the occupation of angular momentum modes, not only to make cool videos, but also perform information processing. And second is we're working with a trap that's fabricated at Sandia. So it has a lot of electrodes that can be used for shuttling ions, splitting ion chains, and merging them, and showing coherent control while all that's happening. And with that, I will open the floor to questions.
We can take some questions now. So, Sara, I didn't get a sense of how you place these nitrogen vacancy pairs in the right place in these waveguides.
Yeah, I didn't really talk about it. That's why I didn't get a good sense. So in my work, it was all done randomly. So we start with a pure diamond substrate and then implant nitrogen ions at the right depth so we can control the energy of these nitrogen ions as they hit the diamond surface, so we can control the depth, but we don't control the XY placement. So in these structures, they were just randomly made, and then we looked through all of them to find the one with the NB center at the right place. So other people in the group have done implantation through apertures, and there are other people in the group also working on mapping out where the NB centers are and then fabricating over the NB centers. But that was not a focus of the work.
More questions? Yes, hello.
So you said, thank you for the good talk first.
Thanks.
So you said that you haven't found the transistor of quantum information. So you think it's diamond?
It's a good question. It's a tricky question. I mean, I moved to ions, so I would say that I'm not convinced either way yet. Yeah, maybe ask me in 5 years. So we now have a lot of systems. There are a lot of options that all have different pros. So with NB centers, they don't need as much infrastructure, but they're also not great quantum systems. Where ions are great quantum systems, but need a lot of engineering to build up the numbers. So, not gonna bet. Not gonna make a bet.
More questions?
In your measurement setup, you also need to excite the NVs with microwaves, right?
Mm-hmm.
So how do you do that? I didn't see it from the measurement setup.
Yeah. So now, so in this work, we really just took a loop of wire and brought it pretty close to the NV. It was pretty crude. Just take a loop, hook it up to some, RF source, and bring it as close to the NV as possible. You have some radiation. It's not at all optimized. You can also fabricate strip lines directly onto the diamond or directly onto the photonic integrated circuit. Yeah.
More questions? Okay. If not, Sara, congratulations again for this distinction. Good luck on your postdoctoral studies in Berkeley.